Ang advice sa akin ni Dr. Hermosa is ipi-play na lang itong ano na to, itong mock defense na ito. Tapos I'll be there na lang to answer some questions. Carry lang. Ang
Yes,
advice
sir.
sa akin ni Dr. Hermosa is ipi-play na lang. Ayan na, nagdo-double yung sound. So naka-live na tayo ngayon. Alright. So, meron pala akong ipapadalang link sa inyo. Link, ilalagay ko sa baba. Kasi kasama yan sa ano. Kasama sa script. Paano ba ito? Ayun. Sorry medyo ano, matagal. Pwede ko ba ninya patayin yung YouTube? Kahit na ano, hindi naman maapektuhan yung live, no? Kung i-close ko.
Yes. Ako na lang din to check if okay.
Kasi masyadong malaki yung data ko. Kapag ganun. Anyways. Alright. Ang problema ko, kailangan ko pala yung link. So, ito yung link nasa baba. I-chat ko. So, kung may manonood sa link, nood lang sa link. Tapos, maglalagay ako ng picture in your computer. Paano ba pinipin yung ano? Pinipin yung comment?
Hindi ata yun pwede.
Hindi pwede yung pin.
Hindi.
So, ikaw yung magiging co-host ko niya, diba?
Yes.
Kaya mo bang i-ano yun? Tawag dito? Yung ikaw yung mag-send ng image na yun.
Anong image?
Anong image? Eh lang, nawala yung ano, nawala yung arrangement ng gulo. Naka-arrange siya na. Wait lang Naka-arrange siya differently. Mada-download mo to kapag nandyan na. No?
Yes.
Oo. Ito. 41 pala. Ay, ba't nakaganon? Ba't sa'yo ko lang na-send? Sa everyone dapat. File. Yung 14 na. 14. 14. Ito. 41 pala, hindi pala 14. Ayan. So, ayan. Yung file nasa baba. Hindi siya naging picture for some reason. Dapat naging picture yan. Ayan. So, I think pwede na tayo mag-start.
Okay. Good afternoon, everyone. So we're here to witness the dissertation presentation of Mr. Renish Simon, entitled something. So the panel members consist of Dr. Arnel Salvador, Dr. Valerie Samson, Dr. Cesar Saloma, Dr. Hio Santos, and the advisor, Dr. Nathaniel Hermosa. So, Mr. Simon, you're given 1 hour to present your dissertation. You may start anytime you're ready.
So, let me share my screen. So, is it visible?
Yes.
Alright, let me start. So, good morning. My name is Ren Simon, a PhD physics student under the mentorship of Dr. Nathaniel Hermosa. So, this venture is funded through uh, his DOST shared project entitled Angular Gaussian Shift, an optical phenomena for ultra-thin thickness measurement, and also through his Balik PhD program of the University of the Philippines. This thesis is not possible without the contribution from the awesome people. Uh, from these awesome people, Jenny Lu Sagisi, a PhD MSc student and a photonics lab member. Jenny served as an SRS for this project. Nina Angelica Zambale, a photonics lab member and a faculty member, and a PhD physics students in NIP. Also, Judd Snarag, a graduate of MS Physics in NIP and currently a PhD student in the Technical University of Denmark. He served as an SRS at the same time as Jenny. So to give you an overview, we arrived in this research after we stumbled upon the question, is a single layer graphene a slab or a perfect sheet? So as we seek the answer using the available resources in our laboratory, we learned that the standard angular reflectivity analysis is not enough to reveal us the answer. So we developed a technique that led us to this dissertation, the crossing angle measurement as thin film characterization technique. So my dissertation has 8 chapters, and these chapters can be grouped into 3 major clusters: the foundations, experimental, and synopsis. The main results in this thesis are presented in uh, chapters 3, 5, and 6. In chapter 3, I will present a matrix formalism we constructed to analyze our experiments. Our experimental results on a standard thin film will be presented in chapter 5. And lastly, our investigation on graphene will be presented in chapter 6. So let's start with light. So light carry information. It can carry information and it enables us to explore both the big, like our universe, and the small, the world of molecules, atoms, and the subatomic. With light, we explore the nanoworld, and one of my interests in this world is thin films. So thin films are everywhere. We can see it. With it, we can see our world in different colors. For example, a thin film of oil creates this glamorous interference hues. Thin films also give a new color to living things, just like the case of this Japanese jewel beetle. So a beetle may have green pigments, may not have green pigments, but it can still appear green thanks to the stock of thin films they grow on their exoskeleton. So we mimic this technique in nature to produce mirrors that can select a particular wavelength to reflect, and we apply it to our optoelectronic devices such as solar cells. So with thin films, we produce better light absorbing surfaces to divert sunlight energy into a use we want for it. So in the field of optoelectronics, we use thin films for various of reasons. So first, for economic and for its lightweight properties. So they are cheaper and lighter because compared to its bulk counterpart, because they need lesser amount of material to produce. So thin films are just beneath the surface and can easily be characterized and modified. And lastly, they offer new functions that not available in their bulk counterparts. So they are now being used for infrastructures and aeronautics as anti-ice and anti-protective coatings. Thin films are major parts of energy generating and storing devices. Also, they are essential parts of our electronic devices such as transistors and LEDs. So currently, the society is demanding for devices to come in small and smaller sizes. So this is why we continue to develop nanotechnology such as thin films. So we utilize thin films depending on their properties. So when we can know its properties, that's the time we can precisely tweak them into the use we want for them. So we examine optical thin films in various of ways. So the National Institute of Physics houses some tools for thin film characterization. Naming some, we have scanning electron microscope, X-ray diffractometer, uh, Raman microscope, photoluminescence spectrometer, UVV spectrometer, and my favorite are the reflectivity measuring devices. So my dissertation focuses on this technique due to the following reasons. First, reflectivity has a stronger signal compared to emission-based techniques. And second, wavelength and position dependence can be incorporated in the setup easily. Third, it can probe dielectrics, insulators, and metals. And lastly, it is non-destructive and requires only simple sample preparation. So reflectivity-based measurement technique can be done as simple as taking the intensity ratio of the reflected light versus the intensity of the incident light. So here, I show curves of the angle-dependent reflectivity by a gallium arsenide substrate. The illumination wavelength here is 633. So we can analyze the sample by looking for some features like the minimum of the P reflectivity located at the sample's pseudo-Brewster angle. So the special angle can be used to identify the sample's optical property. Well, in this thesis, we develop a technique based on a new angle we call as the crossing angle. So at the crossing angle, the degree of polarization of the reflected light vanishes. So this new angle have properties such as wavelength and material dependence. It will also be discussed that the crossing angle technique is more sensitive to the nature of the material compared to the pseudo-Brewster angle. So what I mean with the term nature is whether a material, specifically the 2D material, is best described by a slab with finite thickness or an infinitesimally thin sheet. This will be elaborated more as we go further in the presentation. So with the crossing angle introduced, I'd like to lay down the specific objectives of my thesis. So number one, I will construct a mathematical formalism that describe light propagation in interaction with thin films and 2D materials. Second, we will build a setup and test the viability of our method in measuring the thickness of a thin film. And lastly, I will use our technique to determine what model to use for 2D materials. So let us continue with a review on the mathematical description of light. So before we proceed, I'd like to show first a short list of the symbols used in this presentation. So E is for electric field, D is for the electric induction, B for magnetic induction, H for the magnetic field. Epsilon naught and mu naught are the electric permittivity and magnetic permeability in free space. while the functions epsilon, mu, and sigma are response functions of a material. The dielectric function, the relative magnetic permeability, and the conductivity, respectively. So take note of the font. The vectors are in bold font. We will also have a separate, a special font for matrices. So the complete list can be seen through this QR code here. It is also available in our chat box, and you can also click the link below. If you are in YouTube, please click the link in the comments. So I'd like to show this set of equations. Perhaps every physicist knows this set of equations, the Maxwell's equations that governs the uh, electrodynamics. We also have materials equations, which tells us how the electric fields and materials interact with each other. So combining the Maxwell's and the materials equations I showed earlier, we can derive a wave equation for the electromagnetic fields. And then using Fourier transform method, it is easy to show that this set of differential equations admit a solution of a form of a plane wave. And this plane wave warrants the wave vector k to be complex valued. So the expression for k, for the wave vector k, is given in this equation. And from it, we can, let me introduce the response function n that relates the wave vector k when the wave is in the material to the wave vector k naught when the wave is in free space. Here, n is also known as the complex refractive index. Taylor series expansion gives us expressions for the real part and prime, and the imaginary part double and double prime. As we can see, these functions are dependent on dielectric function, the relative magnetic permeability, and the conductivity sigma. Notice that when sigma is 0, the imaginary part and double prime vanishes. So the imaginary part tells us the amount of energy a material absorbs as an electromagnetic wave travels through it. And light absorption by a material is alternatively described by the skin depth or the penetration depth. So plugging the complex refractive index in the wave solution, we can see that the wave attenuates for materials with non-zero and double prime. The imaginary part of the refractive index gives us the penetration depth, which tells us how far an EM wave can propagate in a material. So if a wave cannot reach the other end of the material as it travels through it, such material will be considered bulk. So mathematically, a bulk is described as semi-infinite or infinite material. So the refractive index, as mentioned earlier, is a response function. And the relationship between the refractive index and the wavelength is called the dispersion relation. Here I'm showing you an example of a dispersion relation plot. And in this plot, I'm showing the dispersion relation for a silicon crystal. The real and imaginary parts of the refractive index are plotted separately. For the case of silicon, in the visible region of the imaginary part, in the visible region, the imaginary part is low compared to the real refractive index, and thus it can be called a low loss material. Here I compare the refractive index of silicon to with the silicon dioxide. SiO2 is known to be almost lossless material, for its imaginary refractive index is almost nothing, and we don't we can see it's flat here because it's really small. So going back with the fields, it is important to discuss the symmetry between the electric field and magnetic field. From these equations, we can notice that if we take note of the action of the curl, then we can write ZH equals K hat cross E, where Z is called the complex impedance. The electric field, the magnetic field, and the wave vector are mutually perpendicular to each other, and they form a right-handed orthogonal triad for positively valued C. From here, it can be deduced that for a wave traveling towards K hat direction, it can be a superposition of waves with different field orientations for E, as long as the right-handed orthogonal triad is satisfied. Such wave is called unpolarized. On the other hand, a wave is linearly polarized when the electric field is oriented only in one line, as shown in this cartoon. In experiments, linear polarization is achieved by blocking out undesired electric field orientations. So from here, we have now a description of a linearly polarized plane wave. Taking into account energy considerations, for example, for complex fields, the Poynting theorem can be written as shown here. The first term tells us how fields and materials exchange energies. The first term is the energy flux density onto the system. The second term tells us the power delivered by the fields. And the third term is the mechanical power by the mechanical power of the charges. Here S is known as the Poynting vector equals E cross H. Extracting physically meaningful information is done by implementing the time averaging theorem. And if we write our dielectric function as a real function and we put all absorption related functions in J, we can reduce the Poynting theorem to this form. This form of the Poynting theorem is important in understanding light absorption by infinitesimally thin sheets. To illustrate, consider the Gaussian surface enclosing the interface of two bulk media. Also consider the possibility of the surface current exactly along the interface, described as a Dirac delta current. Evaluating the volume integral, then some algebraic manipulation, we can have an equation containing these dot products. And further rearrangement, we have this energy consideration equation. Notice that the expressions that involve the Poynting vector are expressions for wave intensity. For formality, let me define intensity. Intensity is the amount of energy being absorbed, being transported by a wave per unit area across a surface whose normal is collinear with the direction of the propagation. Plugging our intensity definition to our energy consideration. Earlier, we have this equation whose first term is IR over I naught, second term is IT over I naught, and third term is the real part of E parallel dotted to the surface current conjugate over I naught. Each of the term in this equation has a special name. So the first term is reflectivity. The second term is the transmissivity, and the last term is the absorptivity. So to end this chapter, let me formally define reflectivity. So reflectivity of a surface is the ratio of the reflected light, the intensity of the reflected light, versus the intensity of the incident light. So simplifying the intensity ratio, we have R equals the modulus square of the ratio of the wave amplitude of the reflected light and the incident light. So in this chapter, we discuss a mathematical description of light. Along with it, we define some terms like skin depth, bulk material. We also discuss energy considerations for electromagnetic wave propagation that led us into to defining intensity, transmissivity, absorptivity, and reflectivity. So moving on, we are now on the third chapter, and here I will present a matrix formalism for calculating electromagnetic propagation through thin films and perfect sheets. The results here meet the first objective of my thesis. So I'd like to start with showing you the Fresnel formulae, which is perhaps one of the most famous equations in physics. Fresnel coefficients describe the field amplitudes of the scattered waves at the interfacial boundary of the two media. So the Fresnel coefficient enables us to calculate for the reflectivity as shown. This plot is a normal scale reflectivity. Features of the curves can be seen more easily in a logarithmic scale. Here is the logarithmic scale. And here, the dip of the P reflectivity shows the position of the polarizing angle or the Brewster angle. The Fresnel coefficients shown here are derived by matching the tangential fields of the electromagnetic wave in the incident and transmission regions. The fields are usually assumed continuous at the interface since there's no charge or current distribution formed within the interface. However, the physical realization of 2D materials makes us consider these boundary conditions. A flat 2D material can be a source of surface current at the interfacial boundary. So to describe how 2D material can be a source of surface current, let us discuss the perfect sheet. A perfect sheet is a term we use for the model that describes a material as infinitesimally thin sheet. So in the work of Zahn et al., they modeled a single layer graphene as a conducting perfect sheet, while Merano extends the model, making it applicable to non-conducting 2D materials, such as hexagonal boron nitride. So we ask, what would the Fresnel coefficients look like in the presence of a perfect sheet? And how can we incorporate the perfect sheet parameters in the matrix equations for electromagnetic propagation? So to do that, we synthesize the works of Zahn et al. And Merano and propose a new optical parameter for a perfect sheet. So the response function is derived from the conduction and polarization current generated within the perfect sheet as a reaction to an incident field. Assuming time harmonic dependence, we arrive with the response function epsilon equals to sigma minus I omega epsilon naught chi, where chi is the two-dimensional equivalent of its electric susceptibility. Omega is the angular frequency of the incident light. The response function, the response of the material with the field is summarized by the equation Js equals epsilon E. Then we consider the response function epsilon in solving for wave continuity at the boundary. Suppose we have a system composed of two semi-infinite media, L and M, and at the interface, there is a perfect sheet. So consider the case where the incident field is p-polarized. For this case, the electric field is parallel to the plane of incidence, as shown in the diagram. So for the case of p-polarized incident wave, it is beneficial to express the incident wave in terms of the magnetic field and then solve the electric field using the Maxwell's equations. So the boundary conditions as imposed by the Maxwell's equations are shown here, and applying them for the tangential fields, we can write a system of two equations in yellow color. And this two set of equations can be compactly written in a matrix equation as shown. Notice that the matrix elements are functions of Q and epsilon. Q here is what we call the normal admittance. For p-polarized light, the normal admittance is cosine theta over n. Following the same fashion, we can derive another matrix equation for the case of S polarization. And it is easy to show that the matrix T, which is called the transmission matrix, is given by this expression in yellow color. And each of the elements of this matrix is a function of epsilon Wigel, Q Wigel, Gimel, and zeta. So Q Wigel is just equal to the normal admittance ratio. Gimel is polarization dependent function. It is equal to either 1 or -1. And zeta is just a fancy way of writing our normal admittance. So standard scattering matrix approach gives us expressions for reflection and transmission coefficient in terms of the elements of the effective transfer matrix. So in this case, the effective transfer matrix is just equal to the transmission matrix. So to solve for the reflection coefficient, we have M21 over M11, while the transmission coefficient is equal to 1 over M11. So from there, we derive the modified reflection coefficient for a perfect sheet sandwiched by two bulk media. To retrieve the original Fresnel coefficients, we can simply zero out the epsilon Wigel terms here and here. And this guy also. And that's elegant, isn't it? So we investigate the interaction of the perfect sheet in terms of absorption, reflection, and transmission of light. So here in these two figures, I'm showing a freestanding perfect sheet and a substrate supported perfect sheet. Using the transfer matrix approach, we calculated for the reflectivity and transmissivity of light in a freestanding graphene. Then using our energy consideration equation, I calculated for the absorption. So we also examined the effects of the response function epsilon by considering the time averaging theorem and compare it to the results when the absorptivity is calculated using the transfer matrix approach. And as you can see from this equation, the imaginary part of the response function has a little effect on the absorptivity because of this operator here. And the perfect sheet model tells us also that the electric susceptibility of graphene affects the reflectivity only by a small amount. Now, what if a thin film is incorporated into the system? So we consider a thin film when a slab material as a thin film when its two interfaces are separated only by a distance in the order of magnitude of the wavelength. Considering the absorption of the material, if the skin depth is much smaller than the thickness of the sublayer, then the sublayer cannot be treated as a thin film but a bulk, since the electromagnetic wave coming from its one end won't reach the other end. In the transfer matrix technique, the effect of the wave traveling to and fro a thin film is taken care of by the propagation matrix P. So the phase generated is of the propagating tangential field are contained in the matrix. So the effective transfer matrix for a stratified media as shown in this figure is just the matrix product of the transmission and propagation matrices. So as a rule of thumb, every interface will get a transmission matrix, and every thin film, every propagation through thin film will get a propagation matrix. So with the transfer matrix method, we can derive expressions for the reflection coefficient for a perfect sheet thin film substrate system. So the effective transfer matrix is given by this equation. M is equal to T LF times PF times TFM. And through scattering matrix approach, the reflection coefficient R is given by this expression. And notice that this resembles the reflection coefficient for a thin film. So if there is no perfect sheet, one can just simply zero out the epsilon Wiggle terms, this term and this term. So now that we have an expression for reflectivity for systems with perfect sheet, we can now engage the question, is a single layer of 2D material a slab or a perfect sheet? So to compare the two models, we calculated the reflection contrast or visibility for a 2D material on top of an oxidized substrate. So the definition of contrast or visibility is equal to the reflectivity of the object minus the reflectivity of the background all over the reflectivity of the background. And to compare perfect sheets and slab model, when we a 2D material on top of an oxidized substrate forms a tri-layer when the 2D material is assumed to be a slab with finite thickness. Here, the incident region again is L, and the first thin film, which is our 2D material, is G, and F for the thin film nearest to the substrate, and M is the substrate. And then from here, we have an effective transfer matrix given by this equation, and the effective reflection coefficient is given by this ratio, A gamma over B gamma, where A gamma and B gamma are described by this lengthy equations here. So you might be wondering why oxidized substrates. It is so because incorporating an oxidized substrate, incorporating a thin film, increases the visibility of a 2D material. In this plot, the 2D materials are modeled as perfect sheets. And I'd like to take note that boron nitride is not conducting, making it almost invisible on substrates. But adding an oxide layer improves its visibility, as shown here. So our calculation shows that the visibility of boron nitride is improved when the incident light shines onto the sample at the substrate's pseudo-Brewster angle. So as you can see here, we have here the normal reflectivity and the normal contrast measurements. It's very small, and the two models give almost overlapping curves. However, at oblique incidence, the curves are giving different contrast values and signs. And from here, we can say that for oblique incidence, the slab model and the perfect sheet model are not the same. So to further reinforce this, we plot the spectral contrast with respect to the incident angle as shown in this plot. They predict different contours with thin film model predicting total invisibility of boron nitride at an incident angle equal to the Brewster angle of the boron nitride. We can see it from this line. So at this particular angle here, whatever wavelength you use in the visible region, boron nitride is invisible. And that's the end of chapter 3, where I present matrix formalism for propagation of light through thin films and perfect sheets. And I also showed your sample calculations, which from our calculations, we learned that in silico calculations, perfect sheets and slab are not the same, even for an atom thick material. Now let's move to the experimental part. Let's start with the experimental setup. Here is the schematic diagram of our angular reflectivity. Our light source is a tunable helium neon laser. It has 5 wavelengths, 633, 612, 604, 594, and 543 nanometers. The laser coming out from the source is first directed to a beam splitter, which splits the beam into a reference beam and the incident beam. The intensity of the reference beam is monitored by detector D1. And the reading in D1 is used to calculate for the intensity of the incident beam. So the incident beam passes first through this set of optics. The pair of lenses are for beam collimation. So when we collimate a beam, it makes the beam approximate plane wave. And this is nice because we have a good theoretical background for plane waves. In the second part, we have P1, which is a linear polarizer, which prepares the state of the beam before it enters our liquid crystal voltage retarder, or LCVR. The LCVR allows us to electronically toggle the polarization state of the beam that passes through it. So meaning we can tweak the polarization of the our incident light electronically. The last part of the setup is the rotating stages. The sample holder is placed on top of a smaller rotating stage, while detector D2 is placed at the arm of a larger rotating stage. When the sample's normal is positioned at an angle theta with respect to the beam line, the angular position of D2, that's D2, is set at angle 2 theta with respect to the beam line. This is to ensure collection of the reflected light. Yeah, so here I show in green arrows the path of the laser light before and after it reflects onto the sample. In the experiment, this is the orientation of the plane of incidence, shown in the transparency rectangle. Together with it is a coordinate system. Notice that this coordinate system rotates with the sample stage. So to relate that to our earlier figure on the surface of the sample, so I show here the substrate, the incident light, and the reflected light. So clearly from here, we can see that the angle theta is the incident angle. And as per law of reflection, the reflected light is making an angle of 2 theta with respect to the beam line. So after we have constructed our angular reflectivity setup, we test it with our known samples. So we perform our test by adjusting theta and 2 theta when we do our intensity measurements. So here is an example. If we rotate it, then we can have another set of theta, and until we have a full range scan. So a typical full range scan is from 10 to 80 degrees. This is so because of the limitations in our detector. We have a finite size and we cannot go uh, deeper on smaller incident angles because the incident beam will hit the detector. So near the vicinity of a feature of the reflectivity, we perform a fine scan. So a fine scan has a step size of 0.1 degree. So when we consider the minute possible minute optical misalignments, uh, we declare that our experimental uncertainty is actually 0.5 degrees, and we will be using this to confidently say if our prediction is correct or not. So although the fine scan is 0.1, the uncertainty is 0.5 to take account the minute misalignment. So we test run our setup with various of samples, uh, one of which are the polymer samples. So here I'm showing you a reflectivity plot of a chitosan sample. This is the P reflectivity plot in logarithmic scale. And notice that the chitosan is displaying uh, Brewster angle. So this dip here, this nice dip here, is the location of the Brewster angle. So the other curve is the polyaniline chitosan sample, the reflectivity of the PANI chitosan. So since PANI is a conducting material, we expect PANI chitosan to behave or to demonstrate a pseudo-Brewster angle, which is a behavior seen for conducting materials. So here, the cyan curve and the cyan dots are the theoretical and measured P reflectivity, respectively. And this shallow dip here gives us the position of the pseudo-Brewster angle. So we also test our setup with standard silicon substrate. The plot here gives you the reflectivity of a silicon substrate. And I'd like to take this opportunity to thank Condensed Matter Physics Laboratory Semicon in providing us a bare silicon substrate. So out from the data points here, we can calculate for the degree of polarization of the reflected light, delta R. So delta R is equal to Rs minus Rp all over Rs plus Rp. So here again, I'd just like to reiterate. So every single pair of data point produces a data point for the angular reflectivity as shown here. So this is the normal reflectivity, and this is the angular degree of polarization of the reflected light. So going back to the problem, we want to identify the position of our new special angle, the crossing angle. And the crossing angle is the angle of incidence at which the degree of polarization of the reflected light is equal to 0. So to solve this, or to predict the position, we solve this equation. And the root, the angle root is the crossing angle. So for a bulk material, we expect to find the zeros only at theta equals 0, the normal incidence, and at theta equals 90 degrees, the perfectly glancing angle. However, the case is not the same. if there are thin films, which brings us to this chapter, the crossing angle of thin films. So we measure thickness of a thin film using ellipsometry, usually using ellipsometry, which is the most common standard technique. However, ellipsometry uses complex fitting analysis, and it uses broad light, which is relatively intense compared to laser sources. So angular reflectivity can be an alternative technique. In this case, instead of using the Brewster angle method, we developed this crossing angle method. So the sample we used for this experiment is a standard sample, a silicon dioxide on silicon substrate, which we purchased from VLSI standards. This sample has an oxide film thickness of 102 nanometers, which is measured by the company using ellipsometry. The substrate is silicon. So from here we have this schematic diagram for our sample, and we will be using our reflectivity setup to measure its crossing angle. And as shown earlier, the reflective coefficient is given by this equation, and we will be using the discussed dispersion related curves to predict the position of the crossing angle. So here is our equation for the reflection coefficient. So calculate for the reflectivity, we get the modulus square. And I'm showing in this plot the logarithmic reflectivity in logarithmic scale. And I want you to notice that for film thickness or oxide thickness of 103 nanometers at incident wavelength of 612 nanometers, the two curves intersect each other. And that intersection is the crossing angle. So that's where the S and P reflectivities are equal. So it can be more appreciated when we plot the degree of polarization itself, and the crossing angle is at the intersection of the curve with the horizontal axis. And if we take the logarithmic scale, we take the absolute value of the delta R and take the logarithm, we will have this nice dip here. The dip here is the location of the crossing angle. So we calculated for the position of the crossing angle for different film thickness. So as you can see here, it's sensitive enough to detect sub-nanometer thickness. So that the technique itself is sensitive to sub-nanometer thickness. And we can do these calculations for different wavelengths, different refractive index, and different thickness of the substrate. So here is a two-dimensional plot of the crossing angle as a function of refractive index and film thickness at 633 nanometers. And I'd like to reiterate that our experimental setup has limitations. So the measurable range is only from 10 to 80 degrees. And that is why the crossing angle lower than 10 is not included in this plot since it's not measurable. So as you can notice here, these color bands represents the values of this of the crossing angle. And not every film thickness has a crossing angle. However, the crossing angle, a measurable crossing angle exists on oxide thickness usually used in semiconductor industry. For example, a graphene-based field effect transistor has an oxide layer of 300 nanometers. So to zoom in, so we have here the parameters for silicon dioxide silicon. So for 633 nanometer incident wavelength, the refractive index of the oxide is 1.456. The substrate is 3.881 plus 0.019i. And again, here the thickness, I'm assuming the thickness 102 nanometers. The corresponding parameters are shown by this dash lines, and the cross mark shows you the position of the crossing angle. So the color there represents the crossing angle, the value of the crossing angle. If you change the wavelength, the bands move, as we see here, and for different wavelength, we will expect to have a different crossing angle value. So here is the summary for the 2D plot of the crossing angle for different Hine wavelengths. So for the case of the 543 nanometers, I'd just like to say that it has no crossing angle here. It has no crossing angle. So this is for the 543 nanometers. But for 633 and the rest of the Hine wavelengths, we can measure its crossing angle. So here is an example of the data points we measured using our setup for 612 nanometer wavelength. The white circles here are the data, the measured data, and the predicted curve is, or the matched theoretical curve is the green curve here. So this is the normal scale, and we have here the logarithmic scale. And from the logarithmic scale, we can see here, based from the data, the position of the crossing angle is 70.3 degrees. And if we match our theoretical curve, we can have a measured thickness of 103.0 nanometers. We do this measurement for the rest of the Hine wavelengths. So for my 633 nanometer wavelength, I have 57.7 degrees, and it corresponds to 103.1 nanometer oxide thickness. For 612, I have 70.3. The thickness is 103. 604, I have 72.7 degrees. The corresponding thickness is 102. For 594, I have 101. Sorry, that's not me. It's 80 degrees. I have 80 degrees, and the corresponding thickness is 101.4. So from these values, the thickness, the measured thickness, has an average value of 102 plus minus 1 nanometer. So from here, we can say that our technique can measure at least a nanometer. So with uncertainty of at least 1 nanometer. So here is our summary for this chapter. We measured the crossing angle for different Hine wavelengths, and our uncertainty is giving us plus minus 1 nanometer for an oxide. So again, this is a silicon dioxide. It's non-conducting. The story is different if the material is conducting. So let us now move on to the next chapter, which is the crossing angle of a layered material, layered 2D material. And the term layered here, I just like to emphasize this. The meaning of layered, this is a technical term for 2D materials. It means the 2D material is flat. So such materials are graphene and hexagonal boron nitride. So it is interesting to note that graphene is now being utilized to electronic and optoelectronic applications. And these materials are also being explored in biomedical fields, such as they are used in biomedical fields. Just recently, a paper-based COVID-19 detector is made up of graphene materials. So to properly put these materials into, so graphene is the first 2D material, and it benchmark other 2D atomic crystals. So experiments on graphene becomes the basis for the models for 2D materials. And Games Group in 2007 performed, demonstrated that graphene can be realized. So we use graphene to represent the 2D materials. So our sample is from Graphenea, and this sample has a single layer graphene on its topmost, then followed by a silicon dioxide layer whose nominal thickness is 300 nanometers in a silicon dioxide substrate. So the total thickness of this sample is 525 plus minus 20 microns. In their theoretical calculations, the single layer graphene here has a thickness of 0.345 nanometers. So the refractive indices for the silicon dioxide and silicon material is assumed to follow the values in the literature. Again, we discussed this dispersion relation curves, and we will be using different models to predict the position of the crossing angle of graphene. And from the crossing angle, from the position of the crossing angle, we will identify whether a graphene is a perfect sheet or a slab, which is our motivation in this in creating this technique. So for a perfect sheet, a graphene will be characterized or parameterized by sigma and chi. If it is modeled as a slab, we will be using the graphitic refractive index, and the thickness will be 0.345 nanometers based from the technical sheet of Graphenea. So here are the models we consider in our experiments. We have the slab model. Again, in the slab model, it will be parameterized by the optical index Ng, the graphitic index, and its thickness 0.345 nanometers. For the second model, we have the conducting perfect sheet, and it will be characterized by or parameterized by sigma, the universal conductivity. The third model we have here, polarizable conducting perfect sheets, which is parameterized by sigma and chi-g, where chi-g is the two-dimensional electric susceptibility. So here is the curve, the theoretical curve and the data points from our experiment for 543 nanometer incident wavelength. And as you can notice, we cannot use the reflectivity magnitude to discriminate the three models here because they are almost overlapping. And if we do a statistical calculation, their differences relative to the data points are statistically insignificant. So meaning we can't rely on the reflectivity magnitude alone. So same for the case of 633 nanometers. So we have here the plots for different Heine wavelengths. And so instead using the reflectivity magnitude, I tried analyzing the sample using the pseudo-Brewster angle position. But as you can see here, the position of the pseudo-Brewster angles for different wavelengths, they are almost the same. The three models are predicting almost the same position, and this is within the uncertainty of our measurement. The uncertainty again is 0.5 degrees. So the position of the pseudo-Brewster angle cannot be used to discriminate the three models, which led us to focus on the degree of the polarization. So here is the degree of polarization for a 543 nanometer incident light. And as you can see here, model 1 predicts the first crossing angle at 22.4 degrees, the second model at 21.5, the third model at 23.6. The experiment tells us that the crossing angle is at 22.2. The nearest prediction is given by M1. However, M1 and M2 are within the experimental uncertainty. So we measure the second crossing angle in this location. So we have M1 predicts 50.7, M2 predicts 50.0, and M1 is nearest to the experimentally measured 50.9. And to further reinforce this, we calculate another feature. So we calculated the peak of the curve with respect to the second crossing angle. So the experimentally measured angular separation of the peak and this dip is 10.2. And this is exactly the predicted value by M1. So in the case of 543 nanometers, model 1 predicts the best. For 612 nanometers, model 1 predicts 18.2, model 2 predicts 16.5, model 3 predicts 15.4, experiment is 18.4, model 1 giving the best prediction. So we can do for the rest of the Heine wavelengths. I'd like to note that for 633 nanometer incident wavelength, there is no predicted crossing angle, which is verified also in the experiment. So to summarize, I have now here my, my curve of the crossing angle with respect to the wavelength. And as you can see here, 633 is around here. It has no crossing angle. The open purple circles are the position of the crossing angle. And here's the summary. And for all the Heine wavelengths, M1 predicts the nearest with respect to the experimental measurement. So with this, we can say that a single layer graphene is a slab based on our experiments. So why does it matter? It matters because it means that the fields are continuous through the single layer graphene. And if it's continuous, and if it has a finite thickness, it means that Fabry ferroresonance can occur with the graphene sample, within the graphene sample. And lastly, since graphene is characterized by the refractive index N, it only means that the real part of the electric permittivity, the real part of the electric permittivity is playing a role in the optical interaction of graphene, which is not assumed when the perfect sheet is a conducting perfect shape. So to summarize, I discussed the mathematical description of light, and then we proceed on the matrix formalisms, and then I discussed how we constructed our setup. And then we test our setup with thin films, and then with graphene. So these are the three objectives that I have earlier. And the first objective is met by constructing the transmission matrix. That this new matrix can be used to predict the optical interaction of a perfect shape. And from our calculations, we can say that the slab and thin films are the slab and the thin film, they are not the same. And we constructed our experimental setup, and then we predicted, we calculated for the crossing angle out from this equation. And with our we learned, we measured that the uncertainty for measuring oxide thickness is plus minus 1 nanometer. And for it can also be used to determine the nature of graphene, which is, this is our graphene. And according to our experiment, the graphene is best described by a slab. So we want to continue. We look forward for that this dissertation will lead to another experiments for other 2D materials, and also use our technique in thickness measurement for oxides. Here are the publications related to this thesis. Here are my references. So I'd like to acknowledge DOST Ashtard for supporting me, also for CHED through their two research grant. I am a recipient of this grant, and I'd also like to appreciate DOST Preserved, and they are the ones who mainly fund this project. I'd like to appreciate National Institute of Physics for a decade of research, and Photonics Laboratory for adopting me, and of course, Condensed Matter Physics Laboratory for teaching me how to do research during my master years. And with that, I'd like to end by thanking these three awesome guys from the Condensed Matter Physics, Dr. Elmer Stasio, Dr. Amanda Sumintak, and Dr. Arnel Salvador. I'm now open for your questions. Moderator, are you there?
Yes. So, does anyone have a question? So if meron, you can state it personally or pwedeng pa-type sa ating chat box. Thank you.
Yeah, I have a question kasi kailangan ko umalis. Nice talk, Nini. Nice method of determining thickness using some, ways to by optical characterization, and also providing the model. It's nice. So, observation first. Well, my recommendation is that you have to put. I think you have to emphasize something like in the objectives that you are characterizing, you are using the material, more focus on 2D materials, like something like that. Pero may question ako. First, doon sa ano, theory. So, you have that theory T plus R plus A is equal to 1?
Yep.
Yep. Why is it that it's always like that, equal to 1?
Yeah, it's equal to 1. This is a conservation rule. So as
Meaning?
you can see here, this is derived based from the Poynting theorem. So this is the Poynting theorem. So upon we put some considerations in the expressions for the sigma and the dielectric function, we can have this equation here. This is mainly your absorptivity. So the mechanical energy of the charges is the absorptivity. This has two terms. If you evaluate this, this will give you two terms. This is a closed surface integral, so we consider the light coming into and out from one side and the other side. So if we evaluate this, we'll have three terms that we can rearrange here as follows. So magkakaroon ng three terms. So from those three terms, yun yung magiging conservation condition. It's always equal to 1. And the
Why
fast
is it? Why is it that they're always equal to 1? That's the question. Basically, the question.
This is per 100. So this is always based from here. Hindi siya malinaw dito yung kulay, no? Pero it's a little yung transparency. This is the intensity of the incident light. So this is always in relation to the intensity of the incident light. So the only source of energy for the case we are talking about here is the energy from the incident light. So there are energies that are scattered, there are the reflected and the transmitted, and there are also energy that's being absorbed. So energy conservation requires us that the energy coming from the incident wave must be equal to the absorbed energy and the scattered energy. So if we take the ratio with respect to the incident energy, this one here comes from incident energy over incident energy. So that's why it's always 1 here. So it's like a conservation rule.
Okay, I just want to. This is a theory, basic theory. It means that it's always equal to 1 because everything is not lost and everything is conserved. That's what I mean. That's that's the thing. So second is that you calculate the ratio. There is an error bars. I think sino yung ano mo panel? Doc Arnel.
Doc Salom.
Meron magtaka-instro?
Meron taga-instro.
Na kailangan mong i-justify bakit mo nakuha, paano mo nakuha yung ano? Yung
error.
ano na yan, plus minus 1.
Ayun, yung the fine scan in our setup, you can do a fine scan of 0.1. So uncertainty of 0.5 is used to take into account the minute misalignment. So based on my experience in aligning this laser setup, yung pinhole kasi namin has a finite thickness. So when you align the setup, ang kailangan mo is i-back propagate yung incident light doon sa pinhole. So pag nag-align kami, we put pinhole here. Kaso yung pinhole namin, may finite may finite siyang butas. Finite yung size niya. And malaki, so hindi mo na pwede siyang liitan. So yung
no problem with that. Yung the uncertainty value that you have in the calculated this height, the thickness, something plus minus 1 nanometer, So the uncertainty value of 1 nanometer plus and minus.
So
Yeah.
plus minus 1 based from this. If you take the average, so the average of this and considering the least count of this measurement, you'll have here 102 plus minus 1. So plus minus 1 is based from the deviation from the mean. So the largest deviation from the mean in my calculation is 0.9.
Hindi to variance.
Yeah, since na we can say it's like a variance. Pero yun, kapag kaya mong i-measure yung maliliit na steps ng wavelengths, ganun ang ginagawa ng ellipsometry. So this is like a technique sa ellipsometry. So mag-fit ka and then based from the fit, makakakuha ka ng approximate nominal thickness for the layer. So instead of using the full visible range, I just use the Heine wavelengths. And actually, if you're going to use this for industry application, it tells us that since that we have a plus minus 1 for the Heine wavelengths, so meaning you can just use 612 or just one wavelength, but just take into account that the uncertainty is plus minus 1.
Yeah, I'm just kasi since you have what you call this the Instru group, they are really particular with this. How did you get this value?
Uncertainty.
Error bars. So there must be some statistical calculation. Like for example, variance means that the mean minus the square root of x squared minus the mean, the other x squared, but on the, you know what I mean? Yeah. And so kailangan kasi ano lang kasi yun yung experience ko sa Instru pag nanonood ako ng yung
defense.
Tatanong sila, saan mo nakukuha yung na yan? How can you explain parang qualitatively yung ano na yan? The other question, so dalawang question na lang last. Okay, why is it that it changes this crossing angle, something like that, when you change the wavelength?
Okay. So in this case, for example, in this case, nakahang yun. All right. So this is 633 nanometer illumination wavelength. Since that silicon refractive index changes with the wavelength, so as for the silicon dioxide, if you change the wavelength, then these parameters will change. This band will move because this band is also
function of
refractive index dependent.
Okay. Yeah. All right. That's okay. Last thing is graphene. It's nice. I mean, 2D materials. Yan yung parang sikat ngayon. Because of their what they call this properties, extraordinary, whatever stuff. So you said that you assume that it's flat, right? It's really, really flat.
Mm-hmm.
So the perspective, there's a perspective. It depends. If you are a surface science, so it's not flat. If you read articles, it's corrugated. There's a corrugation, meaning that there is a kind of like a
bump.
something like that in a height like some angstroms, whatever, 1 or 2 angstroms. It depends on the interaction. So layered materials or 2D materials are precisely called 2D materials. It's not because it's two-dimensional in terms of space, but it's doesn't mean the literal term of 2D, but it means that it is their interaction between layer to layer is very weak, or van der Waals. However, recent paper blah 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 stuff, it means that, I mean, for previous 5 years ago or something like that, so it's neglected this kind of like interaction because it's van der Waals, so nobody pays attention on it. Suddenly in 2019 there's a paper called twisted bilayer superconductivity in the twisted bilayer graphene. So when you twist at certain angle, it becomes superconducting. So if we twist at this angle, there's no superconductivity, but you twist in this specific angle, you get superconducting. So it means that there's only how can they become superconducting when they are metal? So the only reason and the only way, the only parameter that you change is that you offset a little bit yung orientation ng in between two graphene sheets. So if you this one and rotate it a little bit angle, it gives you superconductivity. I mean, the theory is, there's a lot of theory on it. It's not solved yet, but it means that this interaction is not, you cannot neglect this one. There's an effect on it. It's so that's why this is not flat, but there's a corrugation, because some point has a strong interaction, a little bit strong, but it's not greater than van der Waals. And then at some point there's a large height that is weaker than van der Waals, so much weaker. That's why you got this corrugation in the system. This corrugation depends on how you grow. So like for example, if you purchase that thing in, I don't know where it is. So typically that, I mean, it's, if that is purchased, it comes from a CVD. So
Yeah.
CVD, you grow it on copper and then etch the copper and then put it in silicon. So that's how you do it. And I mean,
Grown, yeah.
this technique has a lot of effects electronically. There's doping, there's whatever and all stuff. So this affects also your electrical and optoelectronic properties. I'm just saying this based on experience. And also, you mentioned that if FET graphene, right?
Oh yeah,
FET.
graphene, yeah.
How do you construct an FET graphene when it is a metal, no band gap?
They're just using the graphene as an active layer in the graphene and FET. So what I'm trying to emphasize on that statement is that the range of the crossing angle values I have here, the measurable crossing angle values are within the range of values for industrial applications. So for example, yung graphene FET. Graphene FET is usually 300 nanometers. A graphene FET has an oxide layer of 300 nanometers. So that's why most of the manufacturers of graphene on substrates, they offer samples with 300 nanometer oxide layer. So, but the details on how to on the electrical properties of graphene on a graphene FET, I don't know. But there's a person in the condensed matter physics laboratory who's specializing on that. The name is Lorenzo Jun Lopez. He just recently published a paper on graphene FET based gas sensor.
Okay, I just don't understand that how you, because there's no band gap. So the main purpose of FET is that it's band gap. You know, the transistor is band gap so that you can switch it on and off.
Yeah. The when you apply voltage, it will push the Fermi level, and so instead of being a conducting, it becomes semiconducting. So they take advantage of the.
I don't think so. It's so graphene is ambipolar, meaning if you bias it, the ambipolar means it could be N or it could be P. Depends on how you bias it. So if you bias it with positive bias, then you're putting it into N doping. So your Fermi level increases, but your band gap is still no band gap because it's Dirac delta, Dirac cone. Now, if you negative it bias, reverse bias, then you get it P. You lower the Fermi level to the valence band. So, okay, it's very complicated. It can open. The graphene can open, but it's very complicated. You have to put something there. So to disrupt this band, so it will open. Maybe you can put some gold or whatever stuff, or hydrogenate this graphene. So it's anyway. I don't know how they do it, but I'm just asking because anyway, it doesn't make sense to me. The FET graphene, because there's no, that's why graphene is in the dead end, because it's doesn't have gap. That's the problem. If you want to open a gap, you have to put bilayer in it, tri-layer, then it will open. But it's no longer 2D layers or single layer, which has this property, blah blah blah, mobility that they wanted on. Anyway, so I just wanted to tell you this. I mean, I don't know. I mean, it could be. I'm for you. Yeah, I'm for you. I just want to put you in this, that when somebody, someone in the real defense, tell you this, whatever questions or something like that, when you use some terms. So yun lang. I actually like the presentation. It's really nice. You prove mathematically, and then you construct this setup, and then prove it. You support your mathematical construction into the setup, and determine qualitatively that this is the right. You get the right. You can get as accurate as this with the thickness and other stuff with using this method. It's really nice. It's new, so I think it's good.
Yeah, thank you, Dr. Carr.
So alis muna ako kasi I have to go.
Okay, salamat for your time. Thank you.
Walang problema.
Tama ba? Umaga ngayon dyan.
Umaga ngayon. Sige, bye-bye.
Niyaya ako si Jeremy eh. Si Jeremy, daw, madaling araw ngayon doon. Mga, ngayon, 3 a.m., 4 a.m. ngayon doon sa kanila.
Mahirap sa... Pero, congrats, Nene. It's good. I mean, that's why it's mock defense. You have to, be aware. So,
tingnan ko, baka tanungin ako ni Doc Arnel dyan sa FET na yan. In yung research nila.
I don't think so. Doc Arnel, hindi naman siya updated. So, Not sure. Pero ano lang, careful lang, careful. So, but the rest is okay. Very nice.
Okay. Thank you, Kuya Carl.
Ah,
Right.
bye-bye.
So, bye-bye. So, Ninya?
Okay, are
Hello?
there any, sure. Yes, please proceed.
Yan, Dr. Dasalias.
Yeah. Hello, it's Ray Vargas.
Ay, Vargas. Okay.
Hello, Mr. Simon.
Yes.
Hello, Mr. Vargas.
Yeah, I'm Mr. Vargas. I have a question.
Okay. Sige. Go ahead.
You mentioned the silicon, the SiO2 standard from VLSI.
Yes.
The thickness is around 106.
100.
What's the published uncertainty of thickness?
Yeah, the uncertainty is also in some papers that I've read, since that this is measured using ellipsometry, they are claiming that the uncertainty of ellipsometry is 0.1 nanometers. However, in the technical sheet, the number of significant figures they reported is only up to the tenths of nanometers, or even to hundreds of nanometers, and they 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 provided uh, three beam spots, or spots from the on the sample. So here they measured thickness on the top and bottom and at the center. So from there,
And
the uncertainty is around also around 1 nanometer. So
all right.
based from the technical sheet, the uncertainty is from the varying of thickness along the surface of this substrate, not from the ellipsometric measurement.
All right. In your experiment, did you measure also several sites?
What come again, please?
Actual experiment, did you measure several sites?
No. I only focus on the center. So I compare my results with the technical sheet. So at the center, we can do that, but I'm it's really hard to make a consistent measurement uh, for different spots, unlike at the center. So it's really at the center. Measuring on the different parts of the circle, it's really hard to be consistent. So that is why I just measure the thickness at the center. So
All
basically,
right. So the uncertainty of the publish, I mean the published uncertainty is not really related to the uncertainties you reported on your paper.
yeah. The uncertainty I reported is based from the measurement I performed. First, let me show you the summary. The uncertainty plus minus 1 nanometer is based from the measurements with different Heine wavelengths. So the average of these four measured thicknesses is 102, and the uncertainty is plus minus 1. Plus minus 1 is based from the largest deviation from the mean.
All right. Do you have a comparison of the area? Let's say for ellipsometry,
The
what's
beam.
the area, and then for your technique, what's the area? I mean, what's the area involved?
So in their ellipsometry, that Let me check the technical sheet for uh, accuracy. So in our case, the beam spot is around a micron. Our beam spot is around the fraction of millimeters. So in the
Anyway,
so it's
yeah.
really one area. So if there will be a fluctuation of thickness there, it's around that a fraction of nanometer. Sorry, a fraction of micrometer. So yun. I'm trying to access now the technical sheet. So they did not provide beam spot size for in the technical sheet. So for your question, I can only answer the beam spot uh, we used in our experiment.
Yeah, I think you can have some estimation based on, usual ellipsometry setup. But I'm thinking, I believe the area involved is very large, not just several. And then for laser measurement, your the beam is small, right?
Uh, Come again po?
The on your meters, then the spot is very small.
Yeah, we actually yeah. It's fractions of millimeter. So it's around uh nasa micron yeah, hundreds of microns maybe.
Thinking your technique comparing to ellipsometry that your technique could destroy the sample
No.
or not?
Non
Or
So the laser is not focused. It's collimated. So it could destroy the sample if I tightly focus the laser. But in this case, our pair of lens is collimator. So for samples like graphene and semiconductor substrates, it won't destroy the sample. So this is a non-destructive measurement scheme.
all right, thank you.
Thank you.
Thank you, Mr. Vargas. Are there any more questions from the group?
Mr. Timon, I have a question. Hello, Miss Zambale.
Please proceed po, Sir Lian.
Hello, Renish.
Hi, Doc.
Hello, Renish.
Yes, Doc. Yes, sir. I'm here.
Mag-English lang ba tayo dito?
Okay lang.
Pambira si Ray.
Lang doc.
Ano lang, so related sa question ni Ray, up to what intensity kaya natin safely magagawa yan sa graphene? Kasi baka magbago na yung index of refraction niya pag tumaas na yung temperature niya. No need to, hindi naman kailangan magbigay ng automatic answer. But maganda na malaman natin yung parang threshold intensity.
Yeah, I can look for it. So in what temperature yung applicable yung technique. But to answer that, to give you a perspective on how to answer that, maybe I can go with this. uh, slide. You can show this slide. So here is my sigma and my chi. They are response function of a perfect sheet 2D material. So if the intensity of the laser is large, then this sigma and chi becomes a tensor. So epsilon becomes a tensor. So if the intensity of the laser is large, it will demonstrate a nonlinear effect. So in order to know to what extent we can make our laser intense, maybe I can look for this parameter, the expansion of this Taylor expansion of this parameter with respect to the electric field. So usually the nonlinear terms have very coefficient. So, especially for our setup. So it won't give us a nonlinear effect. And we can safely assume that they are just scalars. Ayun po.
Okay, thank you. Another question, medyo technical. What will happen pag merong water vapor in front of the graphene? And kung room temperature measurement mo, malamang meron. Will it shift the crossing angle? And
Yeah.
baka maging tama yung model 2 kapag na-incorporate yung mga water vapor.
Yeah, that's a good question.
Or 3, model 3.
Yeah. Yep. That's a very nice question because there's a possibility that the sample will have water vapor. That's why it's really important that prior
Tissue bago yung na experiment.
yeah, that's why it's really important to clean the sample prior to the experiment. So we keep our the cleanliness of our sample by putting it inside a desiccator cabinet. So that would prevent the water vapor to form a layer of water to form on the top of the surface. And during the experiments, we turn on the humidifier. So that would also lessen the effect. So now, is there a water vapor on top of the sample? So I'm not really sure about it. But to give you an insight, if the water vapor would change the position of the crossing angle, then most likely this won't be consistent. Our result won't be consistent with different wavelengths. So that is why actually crossing angle measurement can be done with just single wavelength. But to show the consistency of our measurement, we perform the crossing angle measurement with the different Hini wavelengths. And the consistency of the result shows that even if maybe there's a water layer on top of our sample, it's not affecting our system. Provided our...
Pwede natin i-check kung nagbabago ba yung index of refraction ng water at the given wavelength. Sana nagbabago para sabihin natin wala masyadong epekto. No? We can check.
Mm-hmm. Mm-hmm.
Kasi malamang 1.33 lang halos yata siya sa buong visible. Tama ba? We can check.
And if there is a thin film of water there, given a refractive index of 1.33, and maybe the layer, the thickness of the layer is very thin, so it won't matter. But in case of the graphene, although it's just an atom thick, it is conducting, so it can greatly affect the absorption properties of the sample. So it can, the presence of graphene can actually shift the position of the crossing angle significantly. So it can override or it can override any effects of the water vapor.
Okay. Panoorin ko na lang defense mo. We support you, ha? Good job.
Yeah, thank you. Thank you, Doc. So by the way, guys, this is Dr. Leon Dasalias. He graduated from PUP, BS Physics. Batchmates kami niyan. Cum laude yan,
Thank you.
and kinuha niya yung
Sir Renz po yung dati, kaya sa ganyan kabait sa amin.
ano?
Kaya po tumataba si Ray. Yan.
Yeah, si
Hello.
Leon, graduate yan ng master's niya tsaka ng PhD niya sa UP, Diliman, NIP. Ayun. Tapos, nag-internship ka sa Japan, right, Leah? So, he's currently
Yes, salamat, sir.
assistant professor assistant, right? Or associate? I'm not sure. In the
Assistant, sir.
assistant
Assistant.
assistant professor in the material science and engineering program of College of Science. So, yun.
Okay lang, sir. Huwag mo na akong ibenta. May trabaho na ako.
Ayun.
Thank you, Sir Nene.
Hello.
We will support you.
Finish.
Yep. Yes, right.
Question, na-highlight ba bakit kailangan tapos na-verify mo ng nag-model?
Yeah, yes. I
Bakit kailangan mag-model?
Okay, very good. That's a nice question. Bakit kailangan mag-model? I guess we need to put it in the slides. So the reason why we need to model is because let me just show you I guess it's nice if I show the manuscript. So here we have implications. So the implication is when the correct model is a slab with finite thickness, then the graphene can be characterized or parameterized by the graphitic refractive index. So graphitic refractive index is enough to describe the slab the graphene. And since graphene is the layers forming the graphite, so it also tells us that the refractive index of graphite does not change kahit natanggalan mo siya ng maraming layers up to the atomic thickness. Also, because of this, wala pala dito, hindi ko nilagay. Alright. Ayun, dito. So, the graphitic refractive index is 2.6 plus 1.3. So, ibig sabihin, even if you have a single layer or a double layer or 3-layer, the refractive index is still 2.6 plus 1.3. And you just need to get the optical thickness, you just need to multiply the graphitic refractive index times the number of layers or the thickness of the total layer. Also, it means that you can have a Fabry-Perot resonance due to graphene layers. So a single layer graphene is a slab according to our experiment. And if it is a slab, it has thickness, so it can demonstrate Fabry-Perot resonances. And if you are going to create devices based on graphene, you need to take into account that a graphene layer can give Fabry-Perot resonance. And also, it means that the electric field is continuous through the boundary. So meaning it has a refractive index. That's one. And the other is yung ating graphene layer, meron, ibig sabihin kasi kapag meron kang refractive index, let me show it here maybe. Pagka meron kang refractive index, siguro kailangan ilagay sa slide to. This guy, the Maxwell's relation. So n is equal to square root of mu epsilon bar, where epsilon bar is the complex dielectric constant or dielectric function. So dielectric function has the imaginary part E double prime and the real part E prime. So in terms of the conductivity and the real part of the dielectric function, so it is equal to epsilon plus I sigma over epsilon naught omega. So in the perfect sheet model, for a conducting perfect sheet, this is not included. The real part is not included in the optical interaction. So it is as if it is neglected or does not contribute anything to the optical interaction. But graphene being a slab, it means that its complex refractive index, both the real part and the imaginary part, plays role in the optical interaction. So it is important when you're making a device based from a stack of graphene. Maybe if you have a single layer graphene, it won't matter. But if you have devices based on stack of graphene, then this will change your design, especially if you're considering beam shifters. So there are researchers now focus on beam shifts due to graphene layers. So if you have a stack of graphene layers and you use a different model for that, so mag-iiba yung prediction mo. And choosing an accurate model for those kinds of very sensitive devices needs appropriate model. So para makagawa ka ng mas magandang design. So ayun po. Does it answer your question, Sir Ray?
Yes po. Medyo mahaba lang.
Ang Miss Universe.
Hindi, ang inahanap mo kasi siya kanina sa introduction, parang.
Yeah, yeah, siguro, yeah, thank you for mentioning that. Maybe I need to emphasize that a little bit on the introduction. So my introduction is like I delivered it for 10 minutes, and I'm really trying my best to shorten the introduction. So, and I want also I also considering to the non-experts watching my presentation. I want to cater them as well. So I'm really making it friendly even to non-experts. Ayun. But yeah, the point is well taken.
Siguro comment na lang din. Wala kang slide number no, sa part.
Yeah, thank you for mentioning that. That's like the end time. Yeah, I'm still looking for a perfect place for the slide number. And yes, really, it's a no-no when you present your slides. You really need to give them a slide number. But yeah,
Equation number.
even the equation number. Yes, yeah, I'll try to put some equation numbers here or even name them. So yeah. Okay. Thank you for that pointer. I'll consider that in the revisions. Is there any questions from the students?
This is just a short one because you've been mentioning that graphene was a slab.
Mhm.
So were you able to measure the thickness of that slab, and is it near to the one that is written on the spec sheet?
So for that question, I'd like to show this. Show this slide. All right. We did not measure the thickness of the graphene directly. We use the theoretical theoretical measured value, or the theoretical value based from the technical sheet. So according to them, it's 0.345 nanometers. Now, what we did actually is we infer that there is really a graphene there. So, is the graphene there a single layer or more than one layer? The answer is there's only one layer in that sample, and we are sure of that because they provided the Raman spectra of the sample. And based from the Raman spectra, it's only a single layer graphene. Now, on all of these curves, we use the thickness of 0.345 nanometers for the graphene layer. And changing the thickness of the graphene layer would shift this dip here. And the consistency of the measurements with the theoretical predictions only shows that the graphene layers thickness there is around 0.34 nanometers. So it agrees with the theoretical prediction in the literature as well as in the value provided by the technical sheet.
Okay, that's it for me this moment. So my questions ba from the students?
Nandiyan pa ba kayo? Na-enjoy nyo ba? Sana na-enjoy nyo. Si Steven, dapat may tanong ka, Steven. Or nahiya ka lang? May tanong ka, Steven? Are you there?
None po, sir.
Nan yung tanong mo. Okay. Sige. Alright. So maybe that's it. Let's call it a day. Ako talaga yung nagde-declare na dapat si Ninya.
Okay, thank you for attending the mock defense presentation, and let's pray for Renish, and at the same time watch it and tune in for the dissertation defense on Tuesday, December 15 at 10 a.m. So yung Zoom details ay ipopost na lang ni Renish. Ayan, so thank you.
It's in the Facebook account of NIP UPD. So if you want to watch the defense, the Zoom details are in NIP UPD Facebook page. So the announcement is made there. Also, I think they're also posting the announcements in the College of Science website and College of Science Facebook page. So if you guys want to attend, know the details, they are provided by the Facebook pages of College of Science and by the College of Science and the NIP. So, ayun. Ano pa ba? Picture.
Ayan lang. So, picture?
Picture tayo.
Yes.
Pwede niyo bang buksan ang inyong camera? Sige, picture tayo. Ayun, no? Si, naka-green ano pa. Kayo, Kersey. Hindi pa ba si Kersey? Ayan, si Ray. Hi, Ray. Unknown player ka, Ray. Ang ganda ng background ni, ni Ariana. Ayan. Sige. Tara, 2 minutes pa. Alright, sige. Ninya, wala kang picture. Picture muna tayo. Game na. Mag-open ka na ng cam mo. Para yung may picture kasali sa raffle. Mananalo ng tawag
Honor
dito.
cell ka naman.
Mananalo ng pasa-load. Kersey, nandiyan ka pa? Wala niya yata si Kersey. Tara niya, bilisan mo din ha.
Pa ako dyan, sir.
Ayan. Ninya, ikaw na lang. Sayang wala si Karim. Maganda sana ako si Karim. Si Doc Car. Hala, against the light. Unknown player ka niyan. Unknown player. Alright, sige. At count of 3. Doc Lian. Sama ka naman. Yan, okay. 1, 2, 3, and... Alright, thank you guys for being in this math presentation. I appreciate this. Thank you, Mama. Chup chup. I'll end the meeting na. Bye-bye, guys.
Bye. Congrats.